But let me just share the screen while I'm doing that. So this is second last lecture. So next week we are going to finalize the lecture series. Then we're going to talk more about examination. Right.
Recording in progress.
Okay, so I think this is the slide we finalize our lecture last time. And we have been talking so far about the receivers, I think how they look like and what components are there. And then there was one big block we have not spent so much time on is called digital signal processing. So digital signal processing in itself could be a couple of courses. So I will just talk about applications in coherent optical digital communication systems. We had already some material covered in lectures when we were talking about intensity modulation direct detection systems. So there we looked in the different parts in these uh, different parts in optical the different parts in signal processing routines, what needs to be done, and then we look how this could be implemented with digital signal processing. So here I have one visualization what is happening in these different parts of digital signal processing. So in this image, if I show, so what we see here, it's an image from a book, and then it's covered there. So we've been looking at optical front end, which it has optical hybrid, where we can mix a local oscillator and incoming signal together. Then it also includes, in case of polarization multiplexed signals, you have 4 pairs of balanced photodetectors. After balanced photodetector, after pair of balanced photodetectors, there's transimpedance amplifier, and these two are for I and Q in V polarization, and this is for I and Q for H polarization. So these are just two orthogonal polarizations, polarization states which propagate in fiber, and orthogonal means that these functions do not interfere. So then it can be used as an independent channel. So what happens here is that we don't really control a state of polarization in a fiber. So in practical lab experiments, one may use a polarization controller. In case you only work on one polarization, then you could optimize that you could maximize only one polarization. And it happens that if you tune the polarization state, then the electrical signal for these two photodetectors is just going to be maximized. So in what we do this is after this ADC. So then this would be analog to the digital converter. In we have what we use in the lab. It's called digital storage oscilloscope, but in principle that's an analog to the digital converter with a certain bandwidth and sampling rate. So we can get how to say different number of samples depending on input signal symbol rate, and when we sample it, whether we get 2 samples per symbol or 1 sample per symbol, right, then this white part is hardware part, Then the rest is in a blue part. This is how to say, this is software side already. So in experiments we do in research, we usually have an instrument here, and then we collect signals at this place, and we can record them as samples with a trace for each of these electrical signals. Uh, so we have electrical voltage samples equidistantly spaced. So we have a number of those samples depending on a sampling rate and a memory we use in oscilloscope. So in principle, this can be loaded to MATLAB and or Python or whatever signal processing. And also in your simulations, this part is also emulated, and then you can look at these time traces if you install these simulation software also on your computer. You can look more detailed in how the signals looks like and how you get from this cloud to back to 16 QAM constellation points. So and also in practical systems, then these functions are implemented in ASICs, in application-specific integrated circuits, and these signal processing which we do, then we run on one sample per symbol on a full speed. So in practical systems, that is not possible. ASICs with that speed is very challenging to make. So they process signals in blocks. Well, in MATLAB, we also do process things in blocks, or we applied some sliding window approach. So yeah, there are different ways what you can do, how you can process these samples you get. And then there's a certain things you need to do to recover a signal back. So first thing first is like desqueuing. So desqueue means that there's a delay in each of these branches, and this delay can be different. So therefore, you need to fine tune this delay here. So you synchronize all these IQ data, because there can be skew coming from this part only here in the receiver. There can be skew coming in transmitter, because let me just come back to one picture of a transmitter. So here we see also four channels coming here. So electrical signal in each path coming to the modulator can have a different propagation time. So which means that you might have a skew in your signal, and there are different ways how to optimize that, and there are ways how to compensate that. We are not going to cover all the possible sources and how to tackle those sources. There are plenty of research papers available that cover this each of these topics. I mean, on phase recovery, I even had a PhD student who did a full PhD thesis back in KTH. So just on phase recovery, and other students spent another thesis on studying frequency noise and its impact on digital signal processing or just a communication system. And these topics are quite can be quite wide, and you can dig very deep, because when you do practical implementation in an ASIC, you need to do different how to say compromises, and then eventually you still need to get acceptable bit prefec pre-forward error correction bit rate value. So that is what we also look in at the output. You get decision and decoding. You get bits, and then you just count errors. How many errors you were got in the bits. Right. So this queue, so we were talking about this queue. So this queue can be either transmitter or receiver. Uh, then there is orthogonalization, so which needs to be like then you kind of make a complex signal out of I and Q. So you have then you can make a complex and when you have a complex signal made out of these I and Q, so uh, real and imaginary value of a complex number. So here you're already dealing with complex numbers. And when you have a complex numbers, uh, then you have access to both amplitude and phase. And this is the biggest difference between uh, how to say uh, intensity modulation direct detection systems and coherent optical digital coherent communication systems, because in intensity modulation direct detections you're dealing only with intensity. So basically you maybe get an amplitude value, well most likely in intensity value, but you don't get the phase part. Here you can get the phase part. And why this is so important is that when you get the face part, then you can do more accurate, for example, chromatic dispersion estimation and compensation. So basically, uh, this is the reason why coherent communication systems became very widespread. It was first thanks for developments in ASIC technologies around 2000s, a little bit later when the first 100 gig coherent system came out commercial. So ASICs, that was the developments which helped to implement these all different points. And yeah, there was quite many works also on chromatic dispersion estimation and compensation. So and this chromatic dispersion estimation and compensation can be done in different domains. So basically you apply filters and you can do this in time domain or in frequency domain. And there are different pros and cons. I'm not sure how deep how much I have on this later on, but what I would like to say, just rule of thumb, for example, if you have a very long link, then doing time domain chromatic dispersion estimation would require a lot of taps in a filter to describe the impulse response of the system. Well, but if you are using frequency domain compensation, then this is easier for and you can do it less complex for longer distances like 10,000 kilometers. Right. And then when you have done all these until clock recovery, so and clock recovery is that when you have incoming signals and you do this sampling. So basically, maybe I draw something. So if we have a like just a sine wave signal which is coming in here, uh, we assume there's no modulation, so we be two lasers, and then the frequency difference is like on a tone, so we get something like this. Okay, different color. So, and what happens here in analog to digital converter, we just sample it. We get these samples. And here we assume that, well, this is our axis, so this is the start of the signal. But the thing in practical systems, we don't know when we are gonna start to start to sample. So we need to find at least the closest sample to the sampling instant, and also try to match, okay, where is the symbol starting. So this is why clock recovery is quite important. So you know, okay, with which bit or which symbol, where are you? And you can, how to say, synchronize also I and Q, and you can synchronize both polarizations as well. Why this is so important? So why do we do clock recovery now? I mean, there's these steps are quite important, and there are for a reason. So, like first fixing skews in transmitter receiver, then you do orthogonalization, and then CD estimation and compensation. But then clock recovery, you need to synchronize both polarizations. So here you kind of synchronize both I and Q, and then you can make them in complex signal. After you have compensated for chromatic dispersion, you can do that. But the next step is what we call adaptive equalization. There are different ways how this equalizer structure could be called. It's also called the butterfly structure. So you are using both polarizations of the signal, and you sum them together. There's adaptive steps. Uh, what happens with this equalizer is that before this equalizer, our constellation looks like a point cloud. Uh, and even if the chromatic dispersion is compensated, still and there's a clock recovery done, still due to so what happens is that we still have some bandwidth limitation in the system, so we will get something noise like signal, even though it's already in an inner circle, so it's not like square with just the noise. So there is some signal, and what is important that when you use I and Q, then you can really so in principle. If you don't control polarization state here, then you do this with this equalizer here. Because what can happen if you don't rotate correctly this two orthogonal polarization states, so you hit this polarization here and this polarization here, so you get combination between two polarizations in each of these complex signals. So with this butterfly. So that's why also you see it as a noise. So because some symbols are mixing from two different polarizations, half of here and half is here, or 30% is here and 70% is here, and vice versa. So what you do with this step is that you so you rotate the polarization back. That's one thing you do. So you know that symbols for different polarizations are different. So you also see clearly, okay, and then you start to see clearly 1, 2, 3 amplitudes. So because this equalizer as such, it also we looked in IMDD systems that we get very closed eye, and then we can open the eye. So basically, we just compress the spread of the signals for each amplitude, like yeah, and what is left is just the rotation, and this rotation it happens because we have not so well yeah, I'm coming back again to do these two incoming signals. So when you assume and you read the book, there are different cases for wavelength of this signal and wavelength of local oscillator. So there are three different scenarios which could exist. It's like that we use the same laser for both signal, and we split the laser before. So we have a laser here, we split it, and we put a modulator here, IQM. And the important part that the delay in this path and time delay in this part is the same. So then we can call these uh, self-homodyne system. Uh, then there's also uh, well, this self-homodyne, you use the same laser. You can use two different lasers, but then they need to have very small or no line width at all to have a homodyne system. So in practice, we use word heterodyne systems. In heterodyne systems means that the wavelength the wavelength we don't use this approach. Then we use two separate lasers, one with IQM and one local oscillator laser, and then we submit here. In principle, we don't need to adjust the time delay here. Then we have one laser here, which is lasing like at this wavelength, and the next laser is somewhere here. And there is a frequency difference. So if there's a frequency difference, then most likely these are heterodyne systems. And this frequency difference, when you use it it should not be too large. So it should be basically smaller than available bandwidth in your ADC. In practical systems, this frequency difference maybe is in order of megahertz. I've seen you can also tune these lasers wavelength to match to keep them closer. So you can put this frequency spacing quite close, but due to the phase noise and frequency noise as in any oscillator, so this wavelength is gonna drift. This wavelength is gonna drift. So this is a frequency domain, but also in time domain, there we will see something we will see something which is called the phase noise. We're gonna talk about phase noise also later on. So the phase noise is also easier would be to say. So it's very easy to distinguish. If we talk about frequency noise, then it's number of rotations around the axis. So if you have a further distance, then the constellation rotate faster in one direction or another direction. And the phase noise is when the constellation rotate up, down, and at different angles. And that is what we call phase noise. So these two steps are critical, and most practical systems are heterodyne. So these steps are critical to make from amplitude like points in a standstill position. And then when we have these symbols, then we need to get to bits and decisions. We need to decide, okay, this symbol is here, and we kind of put the boundaries. And these boundaries also can be done in different ways. So we just say in MATLAB, okay, points which are in these boundaries are this symbol. Okay, then if there's some symbol here which actually belongs here, then we get an error. And then we had also talk about bits and gray coding and different things. So right. So I wanted to spend a bit more time on this slide just to explain to you different things what happen in there. And then now I have a set of slides just showing what happens if there is some impairments in any of these blocks. So let me just move to the next slide. So yeah, so here is like as I was telling that if you have a frequency difference between transmitter laser and local oscillator, it leads to a rotating constellation. So here is just an example, and there are different things what could happen. So there's always a phase drift, so which we could call a phase noise. So then it drifts in one direction. So if you don't have a phase drift, then you can have stable, more flat signal, just about the rotations. And why this is not just going in one direction, because these lasers, or the laser oscillators, if they have a quite large phase and frequency noise, then this wavelength is not just stable here. Then it is really like alive. It moves in one another direction all the time. And this is done by the second laser as well. So in just matter of seconds, you could have a frequency difference of 10 megahertz, 100 megahertz, 150 megahertz. And depending on how large is the frequency noise, then these differences can be more. So my personal experience in lab experiments is when you get very lucky if you get a frequency offset 0. And if you have a very stable lasers, which can be like fiber lasers, then there could be a very small line width in matter of hertz. Then it's very funny to see that the constellation stays very stable and there's no frequency difference. But in practical systems, we want to, how to say, integrate these lasers and all the components, transmitter, receiver, just in one transceiver. So then we use semiconductor lasers. And as we know, semiconductor lasers, they don't have that good, I'll say, that low frequency and phase noise, right? Okay. So yeah, so then due to the fact that we want to scale up the productions, make millions of units, then it should be manufactured on chips, and so it should be compact. And yeah, but then also there are a lot of trade-offs which needs to be done. How complex the design, or how good the laser should be, and how much complex digital signal processing we can afford to have in this transceiver. Right, so here's another visualization. So, and I mean, this phase noise is really making difficult to recover the phase. So it's just a visualization, because the phase noise is usually large there. And here is some impact when we have a too low phase noise. And here we see that there is so yeah. So let's just try to, so carrier phase, high, medium, low, and then we have a too low phase noise, realistic, and high phase noise. So here we also need to know that what has been done with digital signal processing. So here's like overcompensation of the phase noise, because what happens is that you need to do rotation of this constellation. And when you see that the constellation points, so these are just transitions for QPSK. What we are more interested in is in here, these parts. So this signal doesn't look round, it looks oval, which means that on this direction, which is the phase direction, we have a more compression. So this is overcompensation of phase noise. And then there's yeah, then or the phase noise is very low, then you can compensate. And then the only thing what is left is this dimension, and this is amplitude noise. So and yeah, then there's an optimization between how much phase noise you compensate and how much averaging you need to do, and that needs to be optimized depending on how much really the phase noise is there. And there are something like these cycle slips where you just slip the phase to some other place. So here you kind of, if you can track the phase noise, then you can skip almost all the cycle slips. And cycle slip is happens when your phase noise estimation just jumps up and down or just continue and then continues there. And these cycle slips, they can also create an error there. And if you have very high phase noise, then your compensation, so you get something like these banana shapes. So I'm very bad at drawing bananas, but right. So, and which means that your algorithm is not good enough to compensate for the phase noise there is. So either you use more complex algorithm to compensate for the phase noise, or if you cannot find more complex algorithm, then you need to find a better laser. So just to reduce the phase noise in the system. Right. So, and why do we have these phase noise? So, right. I think now we are moving slightly topics. We're talking about the polarization. And if we have orthogonal polarizations, X, and Y, then if the signal is propagating along the single mode fiber, then the states of polarization, they rotate. And if you just try to observe, then you will get this type of point cloud and then you can use this MIMO, so butterfly adaptive equalizer. This is what we looked in here. We looked in here. So this butterfly equalizer, it is also called MIMO equalizer. So we have 2 by 2 there. And what we can do, so we do just to track back all the polarization rotations in the fiber. So it's not part of our course now, but there's has been several accidents in the Baltic Sea where sea cables have been damaged by anchors of ships and like just completely teared apart the cable. So in principle, with the if you can track the state of polarization in a cable, so you can actually know what is happening with the cable. So currently there's quite hot topic in research that this state of polarization in a fiber for complex signals and this data of equalizer can be used to reconstruct in real time what is happening in a fiber. So basically, fiber could be used as a sensor without using any specific sensor equipment. So what is needed is that you get out this signal from your digital signal processing routines and you use it for monitoring purposes. And I know there are already some companies in the world that will have these kind of products. And I just in April organized a workshop in one of the biggest conferences in USA, and we discussed exactly about joint communication and sensing. And fiber was one of the use cases we looked into. And yeah, so this approach which was first thought, okay, there are a lot of changes in polarization in the fiber. We cannot transmit the signal through without doing this equalization. So then we kind of thought, oh, this is a lot of crap. Yeah, so and therefore we had to yeah, therefore we thought, okay, this is nothing useful. But apparently, this is quite useful data, even though it looks like a point cloud and just noise. So things can be done with the signal analyzing this. Right. Sorry, I just need 1 minute. So here is a bit more of uh, definitions that we can have a X and Y polarization at transmitter, and we have X and Y polarizations at the receiver, and then we can uh, how to say quantify these polarization in ideal channel with the Jones matrix, and they're different for different polarizations. Then we can have a different phase difference, and using this Jones matrix, we can form this S1, 2, and S1, S2, and S3, three parameters, which we can describe any polarization state of the light. Yeah, so then we kind of use this Stokes place where we define these states of polarization, and linear 45, right circular, linear minus 45, and left circular. So yeah, so there yeah, so and these are the cases where you have these phase differences between X and Y signals. Right. Okay, so then there's a little bit of mathematics behind. Uh, Here a little bit about so these are different parts of we already see we have these equalizers, and this is, I mean, chromatic dispersion is done with equalizer. Differential group delay can be done because differential group delay is difference between two polarizations, so we can do that as well. Then polarization dependent loss. It's when one of the polarization experience more loss than the other. It can happen. Some components tend to do that, and then these rotations then can be done with polarization state transformation or using these MIMO equalizers. Right. So yeah, so here is just some visualization when you have X and Y polarizations and how this happens. Uh, so these polarization state rotation, PST here defined polarization state transformation between different polarizations. So what happens is that your Poincare sphere is rotating. So you kind of have uh, you and then you can just uh, define a Jones matrix, and here is like PM. So it's a polarization division multiplexed QPA signal example. Right. Then I was talking about these decision boundaries. That in this case we have a QPSK when all the things have been done, and then we try to detect different symbols. So we first say, okay, this symbol is here or there. So we basically get symbol error rate. We can get that. And then we need to get to the bit error rate. So we can either count symbol errors, and then depending whether we have gray coding or we don't have a gray coding, then we can get either one error per symbol or more. And yeah, so, and also these cycle slips and phase noise, if the signal is processed in blocks, it can result in error bursts. So you can have a half of the block with errors due to phase noise. So then you try to avoid these burst errors in blocks. And yeah, and then one more thing is that we can have even whatever constellation. It's like geometrical shaping is possible. So you can define these in different and then you can define these boundaries as well as you like. And quite a lot of machine learning algorithms are used to define these boundaries. So they're like hard decision boundaries or soft decision boundaries. So soft decision means that what this is soft. It's not only one straight line, that we have a several lines, and then we kind of say the probability with the machine learning algorithm. Okay, this symbol belongs actually here because it's somewhere here or here, or this symbol belongs here or here. So yeah, so there are different ways how to try to identify where this one point, which is symbol, belongs to. And here we have just a visualization of maybe 1,000 symbols. If you, for example, have just 5 symbols, then we will not be able to plot the constellation. So we will just put one point here, one here, one here, and one here, and one here. So that's like 5 points, and this will be all our constellation. So yeah, it takes time to accumulate these results. Right. Then let's look at some other impairments, how the system looks like. So here is like timing skew between I and Q. So if you look here, you can see only I values versus time visible or Q values versus time are visible. Then you don't really see that there's some changes in the constellation point. And here they have very strict that this point here and this point here. But actually, this causes that these points start to look very funny. So they can look something like this. They could be stretched in different directions depending on the skew. And this is if this point here and this point here does not meet exactly at the same time. So yeah, so this can happen and is happening, and therefore it's very important also to adjust transmitter skew, receiver skew in experiments, but in practical systems, they actually calibrate transmitter circuits for skew values. So they know what is the skew, so they can fine tune it in the ASIC when delivering the signal. Right. Then there is one important parameter. If because I was talking about these constellation points being how to say yeah, damaged or not damaged by or just expanded. So there needs to be a metric which is not only bit error rate and but still it is quantitative value. Sorry. Uh, So then we kind of have an ideal constellation point, but then we measure this point somewhere else. Sorry. All right. When the constellation point comes in, then it's quite far from ideal constellation point, and then we kind of can define error vector, and then if we kind of get the error in like an amplitude and then phase value, how far it is, then we can, if we kind of have measured and count it to the uh, ideal point, we get some difference. So error vector magnitude is then defined in percents, for example, where 100% means very bad and 0% means very good, because then the 0% EVM means that it's very close to ideal constellation points. So this is one of the metrics used in coherent communications to estimate signal performance. So right, so there's also a bit more definition of error for Q component, error for I component, and then you kind of can define over number of different symbols. You can define EVM for a single constellation, even though you really look at each point and look in many of these vectors. Right, and then you can look at in XY plane, or you can look in polar coordinates where you have a phase and an amplitude. So there are different ways how to express it. But then I think we need to take a short break, and then we are back after the break. So I'll just pause the recording, and then we
Recording
meet
stopped.
in 5 minutes, okay? Do you still hear me?
Yep, okay.
Good, good. So are you back from the break?
Yes.
Recording in progress.
So then we move on with the lecture. Then we're gonna talk about different things, what causes in degradation of this error vector magnitude. So these are signals plotted in time domain. So this is like amplitude, and this is time and amplitude. So when you start to have a more insufficient bandwidth in system frequency domain, you kind of start to so this is time domain. If you have a frequency domain, this is frequency. This is also amplitude. Then you start to get the bandwidth going down like this, and then you don't use only this part of the spectrum. You use all this spectrum, and then due to this low pass filter channel being a low pass, it's quite typical. Maybe you can even have some ripple here. So then the amplitude decreases quite significantly, and then also the error vector magnitude starts to get impacted because it's further away from ideal points. Well, also you get more noise impact because your signal to noise ratio becomes smaller. But yeah, bandwidth filter is just filtering away the amplitude of the signal. Then if you have this jitter, and the jitter can happen due to phase noise, and then you start to get the signal drifting in a time domain, and then you also start to get larger constellation points in the amplitude. So in time domain, and this is amplitude domain. So here you're more affected by additive white Gaussian noise, and here more impacted by laser phase noise. And that both of these affect the error vector magnitude, so you get larger EVM values. This also can be degraded due to if the channel response has ripple like this, then you have even broader impact, not only noise, but also this ripple is just making the constellation point even larger. So right, then with equalizer you try to guess the response and invert it so you get ideal waveform. Sometimes most often it's not possible to get back to ideal. So right. Then EVM is one of the metrics which could be used, and then you can also estimate bit rate based on EVM. So like we had in intensity modulation direct detection systems, you have counted bit rate and estimated bit rate. We use it quite a bit in experiments, and then for this EVM estimation to be very accurate, then you mainly need to be limited. Well, you need to have these round constellation points. If you have very severely limited by the phase noise, then maybe the EVM might not be accurate with the counted bit error rate. Right, and yeah, that of course depends on what signal to noise ratio you have. So okay, then I have a couple more examples of constellation points where you have different impairments. So let's move looking into what happens if you have IQ imbalance. So where this can come from? This is typically can come from we need to look back to the transmitter. If, for example, amplification here or amplitude here is different than in other branches. So if we just look in I and Q, so you have different amplitude on each of Mach-Zehnder modulators. It can happen in digital to analog converter, in amplifier, or in the modulator design itself. So right, but then when this happened, then you kind of get more wider signal in one direction than in other direction. So your constellation point is not square, but already uh, yeah, already like compressed square. So yeah, and this can be defined in decibels, and so yeah, so this is one of the practical impairments. Mhm. Then there also can be IQ offset, and this is when, for example, you could have a constellation offsetted up and down, so signal and offset. So this is really a DC offset, which could be compensated. So well, also it can happen because the frequency is not really in the center where it needs to be. So this can also happen. And what happens is there could also be orthogonality. If the signal is not orthogonal, then you don't get a square. You start to get something like rhomb-like shapes of the signal. Uh, so ideally, you should have 90 degrees between I and Q, but sometimes there's an here's like 10-degree error, and then you see the constellation looks like in this shape. So this also happens while you're still tuning the biases of the modulators. That could happen. Uh, then we have these also frequency errors, which is like frequency noise, and then there are different maximum frequency error that could be tolerated out of the symbol rate, and you see if the constellation order gets higher than the symbol rate. So maximum frequency error can be just smaller. These are just some calculation as an example. I don't say that all these values matches exactly now if you kind of have practical system, that this number could be different, but the general trend that it's more stringent with higher order modulation formats, right? Then we have also we can define this IQ magnitude error. So we get when we get the error here. So just a different visualization of this constellation with different impairments, and then so we get also a phase error. So this is more like too much. Yeah, due to different parameters, it just defined the so you just have a reference constellation, then you have like these kind of banana shape constellations, right? And what it is cost from? It's from laser. Okay, there's a question. So these simulations, so these are these pictures. What I show here is from an application note from a Keysight website. So these kind of simulations similar could be done also in the this Python simulation software we have, depending on what whether the models are implemented there. There's also VPI simulation software that could be used, but I think more straightforward and more flexibility is with Python simulations to do this. But I think I think I see that there's a very specific interest, so we can discuss after the lecture what else could be what other softwares we could provide. But within this course, I mean, you should really investigate this Python library for signal processing. So yeah, so this is DSP for the receiver, but still there's a signal generation, and you can implement different parameters like different impairments in these transmitters. So I mean, usually you want to make ideal, and then you have some other impairments. So you can yeah, you can really define these parameters in different ways. But I guess software where people have already done things, it could be good. But there are so many parameters to optimize that it's yeah. Okay, but we talk after the lecture about this more. Right. So here we have a carrier phase spectrum. So if we have this phase noise, it just changes with the frequency. We're gonna talk more about laser phase noise, how it looks like, how does it impact. But we just shortly look in different snapshots here. So here is again an example when we talk about this queuing of these signals. So after our optical front-end, transimpedance amplifiers, and analog to digital converters, we have I and Q signals, and they are misaligned. So then we have a skew, and then there's this temporal misalignment. And then when we apply this skew algorithm, so from the red, we shift it to the blue. So it's really a shift in number of samples. And then still we get this 90-degree difference between I and Q. And yeah, and then this is just done by, you can search shift these samples, and then you can find the minimal. I mean, I tell just in basic words, but this Q algorithm is maybe slightly bit more complicated. So you can read about it more in book and maybe in some relevant literature. Right, but then this Q I skew, then then your I and Q is just different with the timing reference, and you can see this in transitions here. I mean, the skew is not that large, so basically you still have these points are flat here, but if you have even more skew, then you will start also to see also here. So that means the skew, and I mean, as we know that in MDD systems, we also want to have this eye diagram here in the center to have the widest opening here and widest opening here. And for INQ, you want to have it for both at the same time. Right. And then just then there can also be this skew between different polarizations, and then you can get polarization imbalance there as well. So each independent channel used in coherent optical communication systems can have a skew. So IQ and then different polarizations. So yeah, there are a lot of timing adjustments that needs to be done in transmitter and receiver circuits. Right. Then we have just some example when you kind of have a raw data, and then you load some noise, and then you process the data, you get constellations, and then you get EVM on average 13%. For 16 QAM is not that bad. I guess it's close to the FEC threshold, and this is from specific test of 400 ZTAR standard, and than how this is how this looks like. So because you need to do noise loading, because in practical system your optical signal to noise ratio is going to be degraded over long distance. So you need to load the noise, so you see, okay, at the receiver how much degradation there will be. Okay, then here we see another visualization. We see different symbols from I and Q, where they end up with different colors. Just a visualization, nothing more to comment. Uh, then I have some examples of uh, pretty state-of-the-art things some time ago. Currently, people are also talking about 260 gigabaud for 16 QAM, so slightly higher. So this is like 1.44 terabit system, 1.92 terabit system. What they show here is this is a 64 QAM constellation. It's an optical spectrum, and here is I don't want to guess. So there you kind of track how this. So you want to make it in the middle. This is like a frequency difference between one laser and another. And here they have a bit rate like 9 e minus 4 or 4 e minus 6. So the constellation points are pretty separated. And this is done also on some observation window. So if you're going to observe the signal for a very long time, then your constellation points will get larger, but then this middle will be a different color. But here we'll have just a couple of points, but still these are your error rates, that if your observation window increases, then you can observe more rare errors that happen not so often. And right. Okay, so I think we looked already on this one, where we looked on just the same representation of what we had before, ADC. You have these two orthogonal signals, then you do chromatic dispersion compensation, clock recovery, resampling, then it's polarization demultiplexing, channel equalization, and then it's carrier phase and frequency recovery, and then you do bit error rate measurement. So there are different methods that could be used here. As I mentioned, chromatic dispersion. It can be compensated using time domain equalizer or frequency domain equalizer. I already mentioned that frequency domain equalizer might be less complex for longer links, but time domain equalizer may be a bit more accurate. Then there's one thing I didn't talk that much about, because this chromatic dispersion compensation can also include or be replaced with a digital backpropagation. And I'm not sure if I have a specific slide on digital backpropagation, but I just would like to mention it, since what we do in, for example, these simulation softwares like VPI photonics, when we have transmitter, receiver, and we have a fiber in between. So we model this fiber in dual polarization signals using Monaco equation, and we apply split step Fourier method to do this. So there's so when we do this modeling, of this fiber, we are solving this equation. In principle, the receiver, one could do inverse solution of this Monaco equation, and and then you can compensate not only chromatic dispersion in the link, but you can also resolve linear and non-linear effects in a fiber. So digital backpropagation is being used to compensate for some nonlinearities, but then you really need to know exactly how the fiber is made and where do you have all the losses and what are the coefficients. So it's not that easy to map the link, but these algorithms have been proposed. They show their performance increase. Uh, right. Then there's other algorithms for clock recovery. I mean, one name to remember is a Gardner algorithm. Then for polarization, Demax and channel equalization, these MIMO equalizers, there are two types. I think first people developed constant modulus algorithm. The difference between constant and multi-modulus algorithm, because the first algorithm was made just for QPSK. So you have a constant amplitude, one amplitude which could rotate. But when you start to work with 16 QAM, as we saw, that there's not one, not two, but three amplitudes you need to deal with. And then you kind of deal for each amplitude, you apply the CMA algorithm, and then you call it multimodulus algorithm. So yeah. Then for carrier phase recovery, there are very different methods. Uh, I think I'm not gonna go through all of them. I have some examples later on a slide deck. I think one worth to mention is blind face search. So I think we're gonna cover this maybe next time a bit more detail with visualizations. But ideally, when you have these circles, then you kind of with blind search you just divide this with different phase steps, and then you just calculate. And depending on how many sectors you have, then you can say, okay, how much phase rotation was there for this specific symbol. But it is hardware intensive, so you need to test all these test phases to see how far the symbol is from the ideal constellation point. Right, and bit rate measurement. So it's really can be direct symbol mapping and counting, and we use this differential decoding. So to have one bit error per every symbol error. Right. Okay. So here is a little bit about chromatic dispersion compensation. So here's one link length of 2,000 kilometers, and so as I mentioned, these chromatic dispersion equalizers can have hundreds or thousands of taps, and depending on the sampling rate and the link length, then there, as I mentioned already for the third time now, that the frequency domain equalization is usually preferred to reduce the complexity. Right. So here is just more examples about for two different link lengths, and it's a magnitude and phase responses of the dispersion compensating filter, and the link lengths are 200 and 300 kilometers. So sorry, there should be a mistake in these descriptions. Clearly, 100 and 200 kilometers, and then we kind of say what is the filter length in coefficients. So you get so this filter is all pass filter, and for amplitude it doesn't introduce any change, but it introduces a phase change. So you kind of get this parabolic profile. And the highest the dispersion, then this parabole needs to be more steep, so it's more compressed. So here is some example of overlap and save method. I will not go too much in details into this, but here kind of you really do need to do this compensation in a specific way. So this is one example, like overlap and save method. When you do Fourier transform, you do equalization, then you go do inverse Fourier transform, and then you need to combine these blocks together. So you have to discard some samples when you overlap. And then, I mean, this also helps you to get the memory from different samples, right? Okay, here's another meta. Here's another. So this is overlap say, and this is overlap and add method. So yeah. Yeah, you can read more detailed in a book about this. And here is also a little bit about the complexity of these multiplications per symbol needed. And you see that these multiplication numbers depends on FFT size and number of symbols. And then you see that these multiplications, they just increase with the link. And also it affects, it also depends on FFT size, fast Fourier transform size. Right, here was the picture I was willing to show you when you have optical fiber and you kind of solve this Manakov equation. Then you can uh, divide and use the split step method. So you divide the fiber in just some meters or centimeters length, depending on how long the link is. Then you just solve each of these steps, and you solve linear part and nonlinear part for each of these sections. And basically, you can also do in one direction, you solve it just to solve solve this equation and model the link. In the receiver, you can also do a backwards, so you can really back calculate all the impacts, and you can get back to the signal you transmitted. So that's the ideal thing, but the systems are not ideal, so there are differences when you do these operations. Okay, and then there's again about sampling. So when your signal comes in, you really don't sample at the best sampling instances. So because you don't know where your signal best sampling instance is. So then you kind of get these phase errors, and you can get frequency sampling errors. So you don't sample at the same rate, at the same frequency. So these are problems which can happen with the analog to digital converters. And yeah, because you would assume that there were ideal cases that at the maximum amplitude, and also at the same times. So these kind of things can happen, and needs to be taken into account. Uh, here then you can do different ways how to do this clock recovery. I just mentioned a couple things in a book. Then I mean, you can do purely analog, you can do hybrid digital analog, or you can do purely digital clock recovery. So and this depends really from different methods in the systems. Uh, so yeah, and then I mean, 10 gigabit systems probably had the analog clock recovery circuit, but currently in some you might have only digital. So there are different combinations. So I don't go too much into details. Uh, right. So and then you kind of have a base point, and then after each base point, you would expect that your samples are there, but you get some fractional interval which you need to compensate for. Right. And then you kind of we can look at three cases when you kind of sample a signal and you get the correct sampling time. Then you have a late sampling time, that you compensate that you sample too late. You're late, or you sample too early. So this can happen. So I think so you need to really correct for these samples to be here, and this is done by upsampling the signal, and then you find the right sample when you upsample, and you can interpolate to find the best here. Okay, so here's some example from Gardner, timing recovery, and these timing recoveries, they're affected by other parameters as well. So here is just an example when you have chromatic dispersion and the differential group delay, so PMD is there. So you can change the you can really the curve changes a lot. So which means that if you have more dispersion or more PMD, then your clock recovery performance may be significantly impacted. Right. So here's just an example how it is done in digital, just visualization. I think I would refer you to the book to read more descriptions about this type of about digital clock recovery. Right. So here is this adaptive equalization, which we already look at. It's like it's like a MIMO structure. So, right. And then here is about the principle of CMA, and what happens is that, for example, you have a different when you do have a bandwidth limitation or something, you might have for ideal constellation point, you might have different points here. So here we show that, for example, we have four different points which are in three different amplitudes. So the CMA algorithm, what it does, it finds the ideal point here in the middle and compresses all these points to that ideal point. So here is some example when you have a multiple amplitudes and then it converges to one, and then this usually it's a training part for the algorithm, and then you kind of discard this data before. So it's called this is the time needed for equalizer to converge. So this is in case for CMA algorithm, and then you can also do it for 16 QAM when you have a multimodulus algorithm. Then you kind of switch this CMA algorithm to different amplitude which is needed. So for different symbol for between three amplitudes here, you need to, because in the beginning you cannot distinguish where the amplitude is, and then you start to distinguish that, okay, this is the state where we need to decide, is this amplitude. Sorry, I need to change the color. Is this amplitude, or this? So basically, you still run CMA algorithm, but you switch between three amplitudes because this is how 16 QAM, they have three rotational amplitudes here. I mean, if you have a different constellation, geometrical constellation size, then you can have more amplitudes here. Right. Then there's also different other methods how to do frequency recovery. So it's like frequency domain and time domain. Why this is important? As I said, these lasers, transmitter receiver, they can be with offset, so you need to know how far they are. So that here's just one idea how this could be done. And you can see here that when you have so you can see you can see that there's a spectrum affected, and when you do this operation raising to the fourth power, you can see that you get the frequency difference. So you see that you would like to do that this when you tune the system that this moves closer to here. But first, in order to know where it is, you need to estimate it. Right. And here's about phase noise. It's really a Wiener phase noise realizations, and depending on the line width. So here is smaller line width laser, and it's a larger line width laser. You see that the phase noise variation is much larger in phase radiance. Like you get quite a big propagation. It and the phase noise actually is it is most critical when you have a symbol rate of a system which is small. If you got higher symbol rate, then the phase noise is less of a problem. Uh, Right, and then we can visualize how it looks like when we have phase noise without additive white Gaussian noise, and when you have phase noise with additive Gaussian noise. So you have this banana shape, which is this is for the phase direction, and this is the amplitude direction. So we see that there's we see these kind of structures, and the phase noise affects more the outer symbols, less the inner symbols. Right. But I mean, it's just a right. You can see in this eye diagram. So so you need to really to estimate this, and we were talking about these. I mean, this phase noise can go in many radians. So basically, when you compensate, you need to be in some boundaries that and then if you get these boundaries, then you need to compensate for these discontinuities to get a continuous phase noise, and you could avoid these cycle slips. Uh, right. I think we are running slowly to the end of the lecture. I just wanted to check how far I wanted to go today. I think I think we are not able to finish. I think there are also some different coefficients for from the book is Viterbi algorithm used for phase noise estimation under different noise because when the system is affected, it's not only affected by the amplitude, but it's also affected not by amplitude noise, but also affected by the phase noise. And then depending which noise is stronger, you do this phase noise estimation in blocks or you use a sliding window. Then you can adjust this window size, and window size means how many samples you process at the same time. If, for example, you have a very fast, a lot of changing in a phase node, then you need to use a shorter block, and that will give you more accurate phase noise estimation. But then if you in the same time have more amplitude noise, then you need to kind of choose which noise source is more dominant, and basically you optimize by looking at the bit error rate, which value you need to look into. I think we should end with this slide because then I think we could come back a little bit to Viterbi and go on to more visualization of this phase noise compensation. Uh, Next thing, frequency noise compensation and so on. Right, so I'll just stop today. I'll stop recording. Then
Recording
I will
stopped.
ask, do you have some questions? I know that today Daria is not here. She's on vacation. So then I would like to check whether there are some questions. I have. If you have some questions, then please ask. then I try to reply them. I think if you have questions regarding to your course project and practical works in Python, please reach out to Daria by email. Maybe there are some questions I can solve, maybe I cannot, but I think it's better that you reach out to Daria. I'm gonna stop sharing the screen. So then if there are some questions, you just please ask. And then yeah, so the next week we have a last lecture, and then we're gonna also talk about examination. About I think I have submitted examination days to Wise Institute director. She was responsible for studies, and then we're gonna talk more about examination, not today, but next week. Okay. Do you have some questions regarding the lecture? Otherwise, if not, then you can slowly disconnect. And then if maybe someone wants to ask question more in private atmosphere, then I will stay here until the last participant.